This is the 8th and final video from chapter 40 on the Riemann integral. And we will do a second example. So we will do part C from example 371. Part A was a linear function. I did that in the previous video. This is a cubic function. Part B is a quadratic function. So it's harder than the first example that I did, but not quite as hard as this one. So I will let you look at example B in the notes and study that. If you have any questions, let me know. But I've done example A, and now I'll do example C. And so we have the integral from -1 to 1 of x cubed plus x dx. And again, we're going to use theorem 314, which is telling us that when we calculate this integral, we have a continuous function, x cubed plus x, on the interval -1 to 1. And that is an integrable function, so we can calculate the integral. And we're going to choose as our x sub I star the right endpoint of our interval, which is, in this case, is the left endpoint plus b minus a I over n. b minus a is 2. So we start with our left endpoint, which is -1, and we take I steps of size 2 divided by n. So we choose the right endpoint of our subinterval as our xi star. We're chopping the interval of length 2 into n subintervals of equal length, so each one has length 2 divided by n. So again, we're choosing the right endpoint, and we're choosing our delta sub I to be 2 divided by n. And so we have f of -1 plus 2i divided by n. We have -1 plus 2i divided by n cubed. That is the x cubed part. Plus -1 plus 2i divided by n. That is the x. And we're multiplying by 2 divided by n. So we take the limit as n tends to infinity of the sum I equal 1 to n of this term. And now we do some simplifying algebraically. So we cube this term, and we have 8i cubed divided by n cubed minus 12i squared divided by n squared plus 6i divided by n minus 1. That is this term cubed. We have -1 plus 2i divided by n that we add. We're still multiplying by 2 divided by n. Here, we just combine like terms, distribute the 2 divided by n through the sum to go from here to here. And now remember, because addition is commutative and associative, we can add in any order. And so if we take the sum, so if we add these terms individually, then take the sum, that is the same as if we take the sum of each one and then add the sums. That's because addition is associative and commutative. Because multiplication distributes over addition, we can factor the 16 divided by n to the 4th out of the sum. We can factor the 24 divided by n cubed out here, factor the 16 divided by n squared, and we did not factor here, but we could have. We could have written that as 4 divided by n times the sum I equal 1 to n of just 1. We did not write it that way, but we could have. And remember, going from this step to this step is simply using our usual properties of arithmetic. We've just used the fact that we can add in any order, addition is associative and commutative, and multiplication distributes over addition. That's just all we're doing from here to here. Then when we go from this step down to this step, we're using our summation formulas. So we have the sum I equal 1 to n of I cubed. Here's our formula. The sum I equal 1 to n of I squared, we have this formula. The sum I equal 1 to n of I, this is our formula. And again, we take the sum I equal 1 to n of 4 divided by n. That is simply 4 divided by n multiplied by n, which is 4. So from this step to this step is our summation formulas. From this step to this step is using what we know about limits. So here we have a polynomial in n. We have a fourth degree divided by a fourth degree, so we divide the lead coefficients. So we have 16 divided by 2 squared. So we have 16 divided by 4. The same thing with this term. We have a third degree polynomial divided by a third degree polynomial, divide the lead coefficients. We have 48 because we have 24 times 2. So the lead term here is going to be 48n cubed divided by 6n cubed. Divide the lead coefficients. We have 48 divided by 6. And we're subtracting. Same thing here. We have a second degree polynomial divided by a second degree polynomial. Divide the lead coefficients. We have 16 divided by 2, which gives us 8. So we add these four terms, and we have 0. So the integral is 0. In the next chapter, we're going to learn why that is. So a little bit of a sneak preview into the next chapter. If you integrate from any number to its opposite, so -1 to 1, for example, -2 to 2, whatever you have, you integrate from a number to its opposite of an odd function, you will always get 0. So the thing that made this 0 was the fact that we're integrating from a number to its exact opposite of an odd function. When you do that, you always get 0 as your integral.